All right, let's dive right into this explainer. Today, we're unpacking Chapter 27, Appendix F, which covers one of the most fascinating, almost mind-bending concepts in all of computer science, recursive procedures. If you've ever looked at a piece of code and felt like you were staring into an infinite set of mirrors, well, you are definitely in the right place.
So think about this. What actually happens when a computer program tries to call itself? How does a piece of software act like a mirror reflecting a mirror without just completely crashing your entire system? I mean, it sounds totally paradoxical, right? A program instructing itself to run itself. But instead of spiraling into chaos, this self-referential technique is actually the secret engine behind some of the absolute most elegant problem-solving in software development.
You know, the renowned computer science educator Daniel McCracken really hit the nail on the head here. He points out that grasping recursion is absolutely essential. It's a fundamental building block, whether you're treating it as a pure mathematical concept, a coding technique, or just a broader problem-solving approach. This idea cuts across so many areas of computing, from navigating complex file directories to sorting massive arrays of data. Here is our quick roadmap for today. We'll start with the core concept, visualize things using activation trees, tackle the wildly deceptive Ackermann function, peek under the hood at memory stacks, and then weigh recursion against iteration.
Okay, Part 1, the core concept of recursion.
Basically, recursion in programming just means a procedure that calls itself. But wait, if a function just kept calling itself forever, you'd get an infinite loop, and boom, your program crashes. Enter the base case. The base case is absolutely crucial. It acts as an emergency braking system. It's a specific, hard-coded condition that tells the recursion to stop and finally return a value. Every recursive function has to have at least one base case, or the whole thing falls apart. Let's ground this with a classic math example, the factorial. You probably remember that the factorial of 5 is 5 times 4 times 3 times 2 times 1. But think about how we can handle this dynamically. If you need to compute the factorial of 54, you don't actually calculate all that math from scratch. You just multiply 54 by the factorial of 53. You let the recursion do the heavy lifting, stepping down one single number at a time until it hits that base case. When n equals 1, just return 1. The emergency brakes engage, and all the answers neatly cascade back up the chain. Moving right along to Part 2, let's actually visualize this with activation trees. To really picture this process, we use what's called an activation record instance as our basic building block. Think of this as a snapshot of the current environment for one specific step in our program. It keeps track of the function's name, the exact parameters being passed into it for that specific round, and eventually the value it returns. This is our fundamental unit of work. Now, apply that building block to the famous Fibonacci sequence, where every number is the sum of the preceding two. To solve for Fibonacci 5, the program logically branches out into two separate tasks, Fibonacci 4 and Fibonacci 3. And then Fibonacci 4 branches into 3 and 2. It creates this beautiful, expanding topological tree where the leaves at the very bottom are those trusty base cases, the simple 1s and 2s that can immediately return a value without branching anymore. But here's the kicker. Your computer doesn't solve this whole massive tree at once. The dynamic execution of the program actually follows a depth-first path. That means the computer starts at the top and then plunges all the way down the left side of the tree from 5 to 4 to 3 to 2, hitting the very bottom left base case first before it ever surfaces to calculate the right-hand branches. It's a very methodical deep dive. All right, Part 3. Let's look at a true mathematical magic trick, the deceptive Ackermann function. This one is absolutely wild. Unlike Fibonacci, the Ackermann function actually passes the function itself as an argument inside its own recursive call. It is literally recursion nested inside recursion. Just feeding it the tiny numbers 2 and 1 creates an incredibly dense, tangled family tree of function calls as the program furiously branches out and constantly updates its own parameters. And the scale of this? It's genuinely staggering. Because of that intense, nested recursion, if you pass just the inputs of 4 and 2 into the Ackermann function, the result explodes so fast that it generates a massive output number containing 19,729 decimal digits. Literally, no way, right? Two tiny numbers go in, and a complete mathematical leviathan comes out. So how on earth does your machine keep track of all this without melting down? That brings us to Part 4, Under the Hood, Looking at Stacks. Welcome to the backstage tour of your operating system.
The secret sauce here is the control stack. Each time a recursive call is made, it gets its very own dedicated memory block called a stack frame. This frame contains a return address so the program knows exactly where to go back to, the new parameters being passed, and a frame pointer to mathematically link it to the previous step.
Every single time that recursive program calls itself, the computer neatly stacks these three pieces of memory right on top of one another, kind of like a tall stack of plates at a buffet. It pushes the return address, pushes the frame pointer, and pushes the new parameters. Then it shifts its focus entirely to that new top plate, leaving all the older ones safely stored underneath. This means the control stack physically grows and shrinks dynamically in your computer's memory. As the recursive tree branches downward, the stack physically grows taller, pushing new frames. Then, as those base cases are hit and the answers are resolved, the stack starts popping those frames right back off, shrinking down until the final definitive answer is delivered to the original caller.
Finally, let's zoom back out for part 5, recursion versus iteration.
You know, it's a proven fact that any recursive algorithm can actually be rewritten using standard iterative loops, like your everyday while or for loops. So why even bother with recursion? Well, take something like a binary search. The recursive version is incredibly elegant, compact, and just mathematically natural to read. Doing the exact same thing iteratively forces you to set up manual loops, manage temporary variables, and constantly track different states. Recursion often just maps way better to human logic. But, and this is a massive but, the clear trade-off is memory and processing time. Calculating something recursively literally builds heavy demanding stack frames for every single step in your computer's memory. The iterative version, it only ever creates one single stack frame and just efficiently updates a variable in place. To break it down simply, iteration relies on looping back and manually updating its state as it progresses, terminating only when a specific loop condition is met. Recursion, on the other hand, achieves repetition by literally calling itself, passing the current state forward as new parameters, and completely relying on that base case emergency brake to stop the chain reaction. Which leaves us with a really fascinating trade-off to ponder. When you're designing software, is the beautiful mathematical elegance and high readability of recursion actually worth the heavy memory overhead and processing tax it puts on your system? It's a fundamental question every developer has to answer for themselves. Thanks for joining me on this explainer, and keep exploring those recursive depths.